Hello, and welcome to the Chapter 3 intro video. Chapter 3 is all about proofs, where we introduce the main methods of proof. And so I thought it was a good idea to record this intro video to just give you an idea of what proof is, what it means to prove something, and talk through a couple examples of proof. So in this video, we're going to talk through a proof of the Pythagorean theorem, and I'll show you my favorite proof of this theorem. In general, there can be a lot of different ways to prove something, but this way I'll show you how to prove the Pythagorean theorem is perhaps my favorite. We'll discuss what constitutes a proof, what should be included in a proof, things like this. And we'll talk through an example of a proof that you could do right now, a proof involving sets. That's not too complicated. All right, let's get started. So let's just take a look at an example of a proof. So what we'll prove here is the following theorem. Let A and B be the lengths of the legs of a right triangle and C the length of its hypotenuse. Then A squared plus B squared equals C squared. So this is, you might recognize this as the Pythagorean theorem, and you may have used this in other math classes, likely you have. What we'll do here is actually prove it. So maybe you've wondered why this is true, how we know that it works for any right triangle, and we'll talk through an explanation of that here. All right, so proof, this is what's considered a geometric proof or a Greek proof. The idea is to build a figure that incorporates this triangle in it, and then compute an area in two different ways. And then show that this equation has to follow, right? So in any proof, we're going to assume some things, and then we'll proceed in a sequence of logical steps that reaches the desired conclusion. So in this case, we're assuming A, B, and C are the lengths, or A and B are the lengths of the legs of a right triangle, and C is its hypotenuse. And then we'll take some steps, and ultimately we'll show that A squared plus B squared has to equal C squared. Let's just take a look at how this is done. So what I'm going to do is I'm actually just going to start by drawing a square with side lengths A plus B. So I'll take those lengths of the right triangle, add them together, and make a square with that as my length. And what I'll do, since the side lengths are A plus B, I'll divide up each length into an A side and a B side. So here's what I mean by that. I'll place this dot here no matter what A and B are, right? Notice I'm not picking a particular value for A and B. It might look like I am, but remember this dot can move around depending on what A and B are. This is just a depiction of it. It's not the only case. It's not the only case of A and B. A and B could be lots of things. So I'm keeping it general. So I'll place this dot to divide it up into lengths A and length B, and I'll do this for every side of the square. A and B, A and B, A and B. Right? So as A and B change, maybe these dots move to different places along the line, but this picture is meant to be general again. And now what I'll do is I'll connect those dots to form a square. How do we know it's a square? Well, in order to figure that out, we should figure out what are the lengths of this rectangle, this potential square. So our assumption is that A and B are the lengths of the legs of a right triangle, and that C is the length of its hypotenuse. Now look at what I have here in my picture. I have 4 triangles, each with legs A and B, and a hypotenuse here. Right? This is their hypotenuse of that triangle. Now, under my assumptions that A and B are the lengths of a right triangle and C is the length of its hypotenuse, I can conclude that if I've drawn it in this way, that this length here should be C. And actually, I won't write that because I have that coming up when I click. So that length there should always be C because A and B are the lengths of the legs of that right triangle. So each one of those lengths is C. Hence it's a square, and we know what its lengths are. So now I have my picture pretty much drawn. What I'll do now is compute the area of the large square. Area of large square in two different ways. So the first way, well, it's a square, so it should be, the area of the large square should be the length of its side squared. So that is, the length of the side of the square is a plus b. So the area of the large square is a plus b squared. And I'm going to go ahead and expand that out because we're going to need it later. So a plus b squared is a squared plus 2ab plus b squared. And now I'm going to compute the area of the large square a different way. So I'm computing the same thing, so I know these two have to be equal to each other, these two expressions I'm going to get. Let me draw a little divider here. There's one area of large square. The other one, well, how else could we compute this? Well, instead of thinking of it as square, I can think of it as these four right triangles and the area of this inner square. So that would be, so what's the area of each one of these right triangles? Well, each one is 1/2 base times height. So I have four of them, so I should get 4 times 1/2 base times height, so a times b. And then the area of the inner square would be c squared. So I also get, and I'll go ahead and simplify this as well, 4 times 1/2 is 2, so I get 2ab plus c squared for the area of this large square. So now I've computed the area of the large square in these two different ways. A squared plus 2ab plus b squared, I know it has to equal that, and I also know it has to equal this, 2ab plus c squared. So it follows that those two things are equal to each other. So a squared plus 2ab plus b squared has to equal, no matter what a and b are, as long as they're lengths of this right triangle, has to equal 2ab plus c squared. Now notice that on either side of this equation, I have 2ab. So I can subtract 2ab from both sides to cancel that off. And what I'm left with, I'll say hence, or therefore, a squared plus b squared has to equal c squared. And now I'm done with my proof. I've reached the desired conclusion, and so now I'll indicate that that the proof is over by drawing one of these little rectangles. Now you don't have to do this, but this is what some mathematicians do to just indicate that the proof is done with, is they'll draw a little rectangle at the end called a tombstone. So let's, just go over this one more time. What happened? Our assumptions were that A and B are the lengths of the legs of a right triangle, and C is its hypotenuse. We used that assumption to build this figure. From the figure, we concluded that the area of the large square was a squared plus 2ab plus b squared, and we also concluded that the area of the large square was 2ab plus c squared, that those two things had to be true. Since we were computing the same thing, we knew those two expressions had to be equal to each other, and then we performed some algebra to reach the desired equation. So that's the idea, and that's how we know, it's one way we know that the Pythagorean theorem is true. For all right triangles, that has to hold. I mentioned before that this is my favorite way to prove the Pythagorean theorem. There's a lot of different ways to prove this. There are other ways to reach this desired conclusion other than the one that I just showed you. So keep that in mind, that sometimes there's many different ways to prove one thing. There can be many correct answers for a proof, many correct proofs, but at the same time there can be many totally incorrect proofs, or proofs maybe that could benefit from some more details or have some logical gaps in them, but nevertheless the theorem is still true. So we'll just go through what I would consider a proof. A proof is a sequence of statements, each following logically from those that precede it and ends with the desired conclusion. So that's a pretty simple way of putting it, but when all said and done, that is exactly what a proof is. There's this idea that each statement has to logically follow from those that precede it, so that means there shouldn't be big gaps in logic. And also, proofs depend on what the audience is. So, like in our class, I'm fine with you using this fact that x squared is greater than or equal to 0 for all real numbers. That no matter what real number you have, if you square it, it'll be greater than or equal to 0. That's something that could be proved on its own, but it's sort of a little bit more deeper than I want to go with this class. We would have to talk about axioms and things like this to really get at why this thing is true. And so you can use something like this. That's okay to use. Or like if another example of this would be like if xy equals 0, then x equals 0 or y equals 0. So you might use this when you're factoring a polynomial that's equal to 0 and you want to identify what the roots are. You would use this statement to conclude that. And so I won't ask you to prove this statement itself, that if a product is equal to 0, then x is 0, y is 0, because this is really just a property of real numbers that's okay to use. Again, this can be proved if we go to a deeper level of real numbers, but that's going to require a lot more work to get to really understanding why this is true. Something that's very intuitively sort of obvious, something you've been using for a long time, I'm okay with you just writing it down and explaining how you get to the next thing. That's okay. That being said, you should always err on the side of explaining more than you need to. Try to get as much detail and explanation in there as you can, but if something just seems really obvious, maybe you don't need to explain how you reach that conclusion. In another sense, what a proof is really nothing more than just an argument. It's an argument for a statement being true or false. But it needs to be logically sound. That's this idea of each statement following from the ones that precede it. That there's no statements that just sort of stand alone and aren't based on anything else. And this argument should be based on definitions, things that we've defined, so terms used in the theorem, assumptions, and axioms. So I mentioned axioms. Things like this we can kind of accept as axioms in our class, that's okay to think of those as axioms and accept these without proof. That's what an axiom is. It's a statement that is considered true without a proof attached to it. It's sort of like an assumption. It's something we're just going to assume is true. Okay, so let's take a look at one more example. Here, we're going to prove something that you could prove right now. It's something involving sets, showing one set is a subset of the other one. But nevertheless, I think it'll be very helpful for illustrating how you might go about proving something. So I won't call this one a theorem. Theorems are usually sort of bigger statements. It's not always clear what we should consider a proposition or what we consider a theorem. Both of these are just statements that we're going to show are true, but a proposition is maybe a little bit lower of a level. It's hard to really identify where the line is between a proposition and a theorem. It's not really important what you call what, in this class at least. So here's our proposition, here's our statement that we want to prove. So let A and B be sets. That's our assumption, assuming A and B are sets. What we want to prove is that the intersection of A and B is a subset or equal to A. So think for a second how you might prove this. And again, a proof is nothing more than an argument. So think, how would you explain to someone that this statement is true? How would you argue with them that this is a true statement? So what you might do is appeal to the definition of A intersect B and appeal to the definition of subset. In order to show something's a subset, I need to show that every element of A intersect B is an element of A. So that's sort of my goal. If I can show that statement, if x is an element of A intersect B, then x is an element of A, then I'll have my proof. So that's sort of my goal. I'm keeping that in mind, and I'm going to need to use these definitions along the way. So let's talk through a proof. First line of a proof might just be establishing the assumptions that you're making. So we're going to suppose that A and B are sets, right? And now we're going to suppose that we have an element of A intersect B. So right, I want to show that if x is in A intersect B, then x is in A. So my assumption here is going to be that I have an element of A intersect B. And what I want to show then is that x is an element of A. Get that? I pretend like I take an element of A intersect B, and then I show that it's also an element of A. That's the idea. Okay, so how do we do this? Like I said, we're going to appeal to the definition of A intersect B. We're just going to write it out as a statement. All right, so we know that x is an element of A intersect B. What this means is that x is in A and x is in B. What follows from that is that x must be in A, right? If x is in A and x is in B, it follows that x is in A. That's true, and it follows from the statement that preceded it. And notice what we've shown now. We supposed x was in A intersect B, and we showed x is in A. So we showed the statement x in A intersect B implies x is in A. We proved that that holds no matter what x is, that statement will always be true, which is the same thing as saying same thing as showing A intersect B is a subset of A. So that's sort of, this is all using the definition of what it means to be a subset. And here it follows that x is in A. Here we use the definition of A intersect B. So it's really just using the definitions to rewrite things, put them in terms of statements, maybe using some properties or some laws of logic to get to the next statement, and eventually get down to showing what you want to prove, which was in this case that we had an element of A. And so this would be a proof of that statement. So I'll end it with a little tombstone. So as you go through this section, you're going to encounter a lot more examples of proof. You're going to prove things on your own, and inevitably you're going to have issues with this. You're not going to totally understand exactly how much detail to put into it. And so this is a good time to work with other students and to come to my office hours and ask me, hey, is this too much detail or is this not enough detail? Does this constitute a proof? Is there anything wrong with this? You're going to need a lot of feedback on this. So make sure you make use of me and your classmates as much as possible while working through this chapter and the next chapter. Okay, that's all I have for this video. Good luck on Chapter 3.